Hello everyone, this is Abilino Dawes, your instructor. Um, in the last lecture, we're talking about the power angular relationship in the generator. So, uh, proceeding, we will consider this new topic on synchronizing power coefficient and later on the solution to our swing equation. Now, as we have learned before, a power system is stable when letter A, power demand and losses are adequately supplied by the generator units, and letter B, frequency is stable and close to its nominal value, and letter C, the voltage is close to its nominal value at all points in the system. And then letter D, generators, transformers, and transmission lines are working within their rated capacity. Now, any small deviation of the load can be addressed by letter A, the governor of the generator, prime mover, by adjusting its set point, as we have also discussed about the turbine generator control. No? And letter B, the automatic voltage regulator or AVR of the generators, by adjusting the excitation, current. The AVR is part of the voltage, the QV control of our generator. Now, a common sense requirement for an acceptable operating point is that the generator shall not lose synchronism when small temporary changes occur in the electrical power output from the machine. Now, to examine this requirement, for fixed mechanical power input PM, consider a small incremental changes in the operating point parameters, like for the displacement angle of our generator, we delta, which is written as delta O plus delta delta, meaning delta O here is the initial operating point of our generator, and then there is a small disturbance causing a change in the angular displacement of the rotor of the generator. So we call this as delta delta. And the electrical power also changes from the initial operating electrical power PEO, because of this additional small change in electrical power. Now, where the subscript O denotes in the steady state operating point values, and delta identifies the incremental variations from those values. Now, substituting those expression into the power angle equation, so therefore for equation PE equal to P max sine delta. So our power angle equation becomes PEO plus PE delta is equal to P max sine of instead of delta we have delta O plus delta delta, and we expand this term here, sine delta O plus delta delta, so that this right side here becomes P max times the sine of delta O, then cosine of delta delta plus cosine delta O times sine delta delta. So this is the expansion of sine delta O plus delta delta. Now, since delta delta is a small incremental displacement from delta O, then sine of delta delta is just the angle delta delta, no? As we can see it even in our calculator, that the sine of a small angle is just the angle itself. So sine delta delta is just delta delta, and cosine delta delta is equal to 1. So the equation above becomes at the left side we still have the same PEO plus PE delta, and at the right side we have P max Okay, then since cosine delta delta here is equal to 1, so we have only okay sine delta O. And then okay for this term, okay we have okay P max, distributing P max to this term here. So P max okay cosine delta O, and then this sine delta delta here is just our delta delta here. Now, however, at initial operating point delta O, our PM is just equal to PEO, no? Meaning, okay, the mechanical power input to our generator is just equal to electrical power output of our generator, assuming, okay, or neglecting, okay, losses. And our PEO is just equal to P max, okay, sine delta O. No? So, therefore, okay, our PEO plus PE delta, okay, is just equal to, okay, PM, okay, plus P max cosine, okay, delta O times, okay, delta, delta. Now, uh, transposing this, okay, to the right, and this one, okay, to the right, to the left, then we have okay we have here a PM, and then this one transposed to the right, so we have minus okay PEO plus PE delta, while this one is also transferred to the left, so it becomes minus okay P max cosine delta O, okay delta delta. Now, substituting delta equal to delta O plus delta delta, and PE equal to PEO plus PE delta into the swing equation. So therefore, we have okay 2h over Ws, or omega s, is equal to the secant derivative of, instead of delta we have delta O plus delta delta, then yeah, we have dt squared. And at the right side, okay, we have okay PM, and then we have uh, PEO plus okay PE delta. Now, however, PM minus PEO plus PE delta is equal to minus P max cosine delta O delta delta. So our swing equation becomes okay 2h over omega s, okay secant derivative of delta O plus delta delta dt squared equal to okay minus, instead of PM PEO plus PE delta, okay we substitute okay this term, which is minus okay P max cosine delta O delta delta. So our swing equation then becomes okay 2h over omega s d squared delta O plus delta delta dt squared. Okay, then we transpose this to the left, so it becomes positive. So P max cosine delta O times delta delta equal to 0. Now, we have to note that, okay, number one, delta O is constant. Okay, so then number two, P max cosine delta O is the slope of the power angle curve at delta O, because our equation P equal to P max, okay, cosine, okay, sine delta. If we take the derivative of PE, we have dPE over d delta, okay, which is the first derivative actually represents okay the slope of the curve, so it's equal to the slope. And when we evaluate this would just be equal to P max, okay, derivative of sine is cosine, so we have cosine, okay, delta. So P max cosine delta is just the slope of the power angle curve, and this is equal to dPE over d delta. Now this slope is designated as okay SP, and this is equal to dPE d delta when delta is equal to delta O, which is just equal to okay P max, okay, cosine of delta O from here. So now this is P is what we call as the synchronizing okay power coefficient. So our swing equation then becomes okay d squared, okay d delta. Now we have now delta now d delta delta, because okay, derivative of delta O, okay, is just equal to 0 because delta O is constant. So uh, in that expression where we have d squared, okay, delta O plus okay delta delta, so we just have okay d squared, okay, delta delta dt squared, okay, as the second okay derivative, no, and then plus okay ws over 2h, okay, times is p, okay, okay, times the delta delta equal to 0. So notice that if we consider delta delta as our variable, and then we have here the delta second derivative of delta delta, no, so we have here okay a linear, okay, second order, okay, first degree differential equation. So this is our okay swing equation in terms of the synchronizing power, okay, P max times cosine of delta O. So now we are going to consider okay the solution of this okay now we will consider the solution to our swing equation, okay, given by okay second derivative of delta delta dt squared, okay, plus omega s times is p over 2h delta delta equal to 0. Now, remembering our knowledge of a differential equation, okay, when we have this type, we usually use the differential operator in mathematics with D, capital D. Okay, so this becomes, okay, d squared times delta delta plus, okay, this factor times delta delta. And then since differential operators can behave like any other algebraic variable, then we can factor out delta delta, and what remains inside would be d squared, okay, plus okay this one, okay, times delta delta. Now if delta delta is not equal to 0, then the factor that we have here, no, containing this squared plus this, okay, must be equal to 0. But using okay the differential operator d, okay, will have no meaning now when we equate this to 0. So therefore, what we usually do is to use an auxiliary variable, let us say variable m, okay, to replace our d, no, so that we can just compute for the roots of our characteristic equation. When we substitute m to our d, then the equation that we have here would be our characteristic equation, and we solve for okay the roots. Now when SP is okay positive, okay, the okay the characteristic equation would be like m squared, okay, plus okay this positive value, and when we equate this to 0 and solve for m, then we will have okay now because we have here m squared, so we have to get the square root of a negative okay value, which is this, and the roots therefore are in complex pair. So when the roots are in complex pair, the form of our solution would be given by this. No? Our delta delta, okay, would just be a certain constant times the cosine, okay, of this okay function, where we have omega in t plus okay a certain angular displacement, okay, phi, where our omega n is equal to the square root of omega s is p over 2h, and this is our angular okay frequency of oscillation, where A, of course, is any arbitrary constant, okay, that will be determined depending on the initial condition of the system. Okay, so when we have positive synchronizing power, therefore, which is to the left of our power angle curve, then we have complex roots, and then the form of the solution would be this one. So, okay, our curve therefore is just a cosine function. No, we are familiar with the cosine function. Okay, so something like this. and then with a certain amplitude, and then with angular frequency, okay, omega n. And with this initial displacement angle, it's equal as, okay, phi. Therefore, the frequency of oscillation is Fn equal to omega n over 2 pi, because omega is equal to 2 pi f. So, solving for f, therefore, we have omega n over 2 pi, and substituting, okay, the values, we have 1 over 2 pi times, okay, omega n, which is omega s, okay, times is p over 2h. And the equation of delta delta corresponds to that of a simple harmonic, okay, motion like a pendulum. So let us have an example here, okay, illustrating, okay, the solution to our swing equation. Okay, now a machine has a power angle equation given as PE equal to 2.10 sine delta, no, and per unit, and is operating at delta O equal to 28.44 degrees. Now, when subjected to a slight temporary electrical system disturbance. Now, determine the frequency and the period of oscillation of the machine rotor if the disturbance is removed before the prime mover, okay, responds. H of the machine is 5 megajoules, okay, per MVA. So we draw the power angle equation, okay, as we had before. So this is our PE equal to P max, okay, sine of delta, where our P max, okay, is equal to 2.1, per unit. So this is, okay, the curve, and then the initial operating point of our generator is this point, okay, corresponding to the rotor angle of delta O, and we have the corresponding electrical, okay, power output of our generator, okay, PEO. So solving for our SP, which is, okay, the derivative of our PE, no? So taking the derivative of this is just equal to, okay, 2.1 times derivative of sine, which is cosine, okay, delta, no? So at delta O equal to 28.44 degrees, our SP would be equal to 2.1, okay, cosine of 28.44 degrees, so this is equal to 1.8466, okay, per unit. So assuming, okay, 60 hertz, okay, system frequency, our omega s is equal to 2 pi f, so 2 pi times, okay, 60, or it is equal to 377 electrical, okay, radians, okay, per second. So therefore, solving for our angular frequency n, omega n is equal to omega s, square root of omega s is p over, okay, 2h. So substituting the values, we have omega s equal to 377, and our SP is 1.8466, and we divide this by 2, and the h is 5, so the answer here is 8.343, okay, electrical radians, okay, per second. So this is the angular frequency of oscillation. Now, the corresponding frequency of oscillation Fn would just be equal to omega n over 2 pi, so it is equal to 8.343 over 2 pi, and it is equal to 1.33 hertz. And the period of oscillation is just, which is t, is just the reciprocal of our Fn, so 1 over 1.33, so this is equal to 0.753 seconds. Now, another case when our synchronizing power is negative, meaning, okay, it is now at the portion of our power angle curve, to the right of 90 degrees, and between 90 degrees and 80 degrees, where we have the slope here, which is sloping towards, okay, the left, and it is already negative. Now, when our S is synchronizing power is P is already negative, okay, now the roots of our characteristic equation, okay, would be, okay, when this is negative, so we have here negative, and when we solve for the roots of our characteristic equation, we will get, okay, real values, no, which are distinct and okay real. No? So we have two roots because we have quadratic, and our first root would be omega n, and then the other root is minus omega n. And when we have okay in our differential equation, when we have okay roots that are real and distinct, then the form of the solution would be exponential. So we have the form of solution delta delta equal to a times e to omega n t plus b times e to the minus omega n t, no, because our roots are real and they are distinct, no, they are different. One is positive, the other is okay negative. So it is okay this form of okay the solution. And where a and b here are constants to be evaluated, and omega n is okay the root. Now omega s times is p over okay 2h. Now we now examining the terms of the solution equation of our delta delta. Okay, we notice that as t increases to infinity, okay, the second term containing b becomes okay 0, which is this, no, the second term, because we have here e to the minus omega in t. Now, as t increases to infinity, okay, this becomes a big number, which is negative. So therefore, e to the minus a very big number, okay, is nearly equal to 0. So this term becomes okay 0. While okay, the first term containing a, this one, okay, keeps on increasing, which makes okay the system unstable. So as t increases, okay, because we have here positive value of omega and t, so this becomes a big number, and so therefore this is this keeps on increasing, no? So this is exponentially increasing, while this one is exponentially decreasing. But the net result of these two is that this one will prevail, no, because as t increases, okay, this becomes smaller and smaller, while this one becomes bigger and bigger. So our generator therefore will be operating okay in unstable condition. Okay, therefore we see that when the operating point of the machine okay goes to the other side of the power angle curve, okay, that is delta greater than 90 degrees, or when the power synchronizing power is okay is negative at this side of the curve, then the machine becomes unstable already. But if the machine is operating at this side of the sine curve, okay, between 0 and 90 degrees, where the synchronizing power is positive, then our machine is stable, no? Because it can just okay swing okay along this curve.